We finish our investigation of the gas laws with two solved problems, one for Avogadro's principle and one for Graham's law. These are relatively obscure laws in terms of the gas laws, and ones that people sometimes struggle with a little bit. Let's begin. This is Screencast 10.6. We have one Avogadro's principle problem and one Graham's law problem. Let's review Avogadro's principle before we dive in, because this is a very powerful tool. It says that regardless of what your gas is, if you have an equal number of molecules, it will occupy an equal amount of volume. The idea is that gases are very small atoms relative to the space that's in between them. That being the case, the identity of the gas really doesn't matter that much. I'm sure it's very close to the same for any gas. The identity of the gas doesn't really matter, and here we go. Here's the problem. What is the density of carbon dioxide gas in grams per liter at standard temperature and pressure? For Avogadro's principle, they always have to say this because it's only true at standard temperature and pressure. So that's a big hint. That's something you might want to make a note of. Anytime you see the words STP, or standard temperature and pressure, odds are it's an Avogadro's principle problem. It has to be said. So we'll treat it as a unit conversion problem. They want grams per liter, and it might not be clear where to start, except that carbon dioxide has a molar mass of 44 grams per mole. 12 plus 16 plus 16. All of these problems involve simply a unit conversion, including 22.4 liters per mole, which can be flipped over. And do we need to this time? Yeah, we have to say a mole is equivalent to 22.4 liters. That way moles cancels, and look at that. Grams per liter spits out. 44 divided by 22.4 is the density of carbon dioxide. 2 grams per liter. A little bit higher than our average of 1 gram per liter, but it's bigger than, say, helium, for example. Graham's law. This says that, I like saying what this is. The rate of effusion of gases are inversely proportional to the square root of their molar masses. Isn't that something? And here it is said in the form of a formula. Or you could also say that light gases go a little bit faster than the heavier ones, but not that much faster. So let's compare helium and carbon dioxide. If you don't know where to start, state the obvious. That means write the formula, and there it is. And we can compare those two by writing their molar masses inversely. We flip them over, and then we do the math. If you put the lightweight gas on top, you'll find it much easier to explain what's going on. And there it is. The rate of helium compared to carbon dioxide is 3.3. 44 for CO2. Helium, molar mass, 4 grams per mole. So there it is. And there should be a sentence here. There really should, this is comparing them, you should say that helium travels 3.3 times as fast as carbon dioxide at the same temperature and pressure, and obviously for the same number of molecules. This is Screencast 10.6.